Okay, so remember what we were doing last time. It was, we were talking about kernel initialization, and essentially we were talking about creating the very first kernel page table. So like I was saying, we started executing inside the main function, right? And we learned how to build the very first page table, right? And remember why we needed it, because originally we booted on this rudimentary page table, which the kernel created at the very early stage of the boot, just to make sure that, you know, it can switch into the virtual memory, right? It only had 2 entries and was mapping from 0 to 4 megabytes, and from 2 gigabytes to 2 gigabytes plus 4 megabytes, right? And so the way it works is that we learn how to build the page table, right? And essentially everything ends with this. And I, like, guys, did you make it to here? Like, did we essentially, were we done with the kv malloc function, which creates this setup kvm function? Did we cover this last time? I forgot already. No one remembers? I think we did, but maybe I'm confused about it. We stop in kv malloc, but did we talk about how the page table is created itself or not? We probably didn't right then. Okay, let me then start over, like from here. So essentially, I remember that we definitely talked about the kernel map, right? So essentially about those 4 regions, right? And I don't remember whether we discussed them in details or not. But essentially, okay, let me a quick recap what was happening last time, and let's just start from here and move fast. So again, so we started running inside the main, right? And what we learned that we can create a tiny virtual memory allocator, which essentially creates a list of available actual physical pages, right? So like if I ask you what memory this allocator allocates, what will you tell me? Which memory? Physical, virtual, which one? Okay, thank you, Matt. Let's just recap quickly. So it allocates physical memory, right? So essentially, remember, we said, okay, well, it accounts for all available physical memory in the system, right? It's a little bit unusual because it doesn't come across immediately that we are talking about physical memory, but really it is, right? So because what it did is that we said, okay, there is this kernel binary, kernel, there's the end of this binary and symbol, right? And we said originally, we just like take the memory right behind the kernel and arrange it as a collection of pages, right? And add those pages to the list of a memory allocator, right? But literally, it's available physical pages. So because the kernel itself most often cares about physical memory. I mean, it's not always true. Like a sophisticated kernel like Linux will allocate virtual memory left and right because it has dynamic number of processes, dynamic everything, right? x86 is much more simpler. So essentially, it does not allocate new inodes, new process data structure. It will only have an array, right? Array of max size, and that's how many processes you can have in a system. Of course, real operating system will not do that, and it will have a real memory allocator within the kernel, right? But x86 just to make sure that the kernel is simple, it just keeps track and dynamically allocates only physical pages, right? And those physical pages are used to create essentially page tables. We're going to use them to allocate physical memory for the text and data section of the processes, to create stacks, right? Stuff like that. And so now we have an allocator, which we say, look, it can kalloc. We call this function, and it allocates back a pointer to a page, right? And so this is one of those pages, right? And we said, okay, since we have an allocator, we can really create a kernel page table now, because kernel page table, we don't really know how much space it will take, right? So it's up to 4 megabytes, right? But we hope it will always take a smaller amount of memory, because we will be allocating those second level pages dynamically as we go, right? So essentially an allocator will be essentially invoked every time we need a new page, right? And so as we map more and more regions, we'll add leaves to the page table, right? Okay, so let's take a look at this kv-malloc function, which essentially creates a new kernel page table, right? So essentially to switch from this rudimentary page table, which I was discussing before, there will be a function which is called setup kvm, right? And it will return a pointer to the root of the page table, like exactly how it's drawn here, right? And then we will invoke a function switch kvm, which essentially will switch the CR3 register from pointing to entry page directory to this new kernel page table, right? Now, this function is reasonably simple. It just switches reload CR3. So kind of like you do in your homework, in homework 4, right? But this function, which is sets up kernel virtual memory, is a little bit more involved, right? So essentially, at a high level, we agreed that we need to allocate a root of the page table with the same kalloc function. We'll set this page to zeros, right? And then we said, okay, we'll be using this map pages function. And essentially, what map pages is doing, it says there's a region of virtual memory and a region of physical memory. And essentially, it starts with the virtual address virtual address. It takes the size of the region, right? The entire thing, so size. And it takes the physical address of the region, right? So this one, physical address. And it will just map the entire region page by page, right? So it will be going forward page by page. We'll be mapping pages one after another, right? And then when we are done, we will return a pointer to the page table, which we created right here, right? So it will be same pointer. But at this point, this page table will be completely populated with leaves, right? And now the question is, what kind of regions we have to map, right? And this is where we stopped last time. So the kernel itself, what it does, it says, okay, I will keep an array. I'll keep an array of pages, right? Array of regions, sorry. And this regions will describe the memory which is mapped inside the kernel part of the address space. And this kernel part of the address space is everything above 2 GB, right? Okay, what are those regions, right? So we talked about it, that we loop through this array, and these are the regions, right? So in general, there are 4 regions, right? So I was mentioning them before. So physical memory starts at address 0. There is some region which is used by devices, like a frame buffer might live here, right? And this region has to be mapped, readable and writable, right? Then there is at 1 megabyte, we map the kernel and the kernel text section. And remember, I told you that we use a specific linking script, and we control the order in which the sections show up, right? So essentially, let me show you like this script right away, because it's worth probably like making sure that you understand where this thing is. So if we go back to project 606 public, and I will show you this linker kernel LD script, right? So it's essentially the script which is taken by the linker. And specifically, we say we will provide a virtual address at which we're linking, right? So it's at 2nd gigabyte. So it's 2nd gigabyte plus 1 megabyte. We say that the kernel, the text should show up first. Then there will be a raw data, read-only data section, right? And here we are providing end of the text, eText symbol. Here we're providing everything like is page aligned here, right? So this is the beginning of the data section, and this is the way to request the linker to say, please provide the data symbol in the kernel source code. In the kernel final, when you link the kernel, so the symbol will become visible, right? So you can actually use it from the source code of the kernel, right? And then copy the data section. So without this, and then copy the BSS, right? Without this wonderful script, linker can actually generate the sections in different order, right? And then this layout, which I'm advertising on the screen right here, it can be actually different, right? But this linker script actually fixes the layout. And we know that kernel read-only data is right above the right above the IO space, right? And the kernel text and the kernel read-only data are merged together, so we can map them together in a read-only manner. Above this, there will be a kernel data section plus BSS, because we just show that there is a BSS as well. And there is all available physical memory, right? So essentially, it will end somewhere around maybe a 2 megabyte, and everything above and up to 234 megabytes, the x86 will say, okay, I will treat this memory as available physical memory, right? And this region has to be mapped readable and writable, right? And finally, there's this additional region, which is, again, belongs to the BIOS and various devices. If you write into this region, essentially it goes to a physical device, right? And we talked about it last time as well. And this one is also mapped one-to-one at the very top of the address space, right? Are there any questions about the address space layout? Everything is clear, it makes sense. Okay, so how we define this array? So array has, this is the array itself, and it's array of structs. Each element of the array is a K-map data structure, right? It has this virtual region start, which I just discussed like a second ago. It has a physical region start as well. So it's essentially, remember I told you that virtual will be mapped to physical, and we need the physical end from which we can compute the size, right? And we need for permission flags, essentially, whether we are mapping the region as writable, whether we're mapping as read-only, and again, these two regions are also writable, right? We can also map with user accessible, but for example, probably it's not very wise, because then the user will be able to access those parts of the address space and maybe corrupt the kernel in some way, right? And this is these 4 regions which I was just talking about. So, right, the first starts from this is physical start, right? So this is physical start 0. Where do we map it? We map it to kernel base. Kernel base is defined as 2 gigabytes, right? And so on. So kernel link is essentially 2 gigabytes plus 1 megabyte. Again, so you can understand how this works. You can look up those symbols in the kernel source code, and you will understand that this is exactly the 4 which I was talking about. Okay, now the question. So how to construct the page table, right? So we're looping through this array. Each element of the array is a region, right? And we pass these elements in the map pages function, right? Okay, so what do you think will be inside this map pages function? How will it work? Who can tell me?
Do a read access and it faults and you add it to that, something like that?
Say this again, you want to do a page fault?
Yeah, and then once the page fault happens, then kind of like fix
We
it.
can react and map the page on demand, right?
Yeah.
No, this is not a bad idea, but remember, we didn't even talk about interrupts, and we know what was running. We booted, we jumped into main, we created a memory allocator, we jumped literally into this function, and this is the call stack on the right here. So main, from main we invoked kv malloc, and from here we invoked setup kvm. Did we set up any interrupts? We did not, right? So then how can we handle a page fault if we didn't yet set up interrupt handlers, right? And this is actually the topic of our second part of this class today, is to set up interrupts, right? It's a good idea, but in a very similar manner, how you say, I will react to a page fault, why not to map the entire region proactively? The question is like, how can you do that? How can you map a region of memory?
Can't you just, so from last lecture, you see whether that page has been allocated some memory from the allocator. If it is not allocated, you define that memory from the linked list. Then you may map that virtual memory. Else, if there's existing one, you update that value.
Kind of, right? So like I remember I gave you the overview and you got a little bit confused, but overall you're right. So what we're gonna be doing is essentially we're gonna be walking every page of the virtual region one by one, right? Essentially the idea here is to say, look, there will be a region of virtual memory, and we'll start with this virtual address. which is right here, right? And there will be a region of physical memory, right? And we'll be starting with the physical address, which is right here, right? So this is PA. And we'll be walking page by page, and essentially we will be looking at the page table. We'll have a specific function, which is called a walk page table directory, right? Which says for this specific address, which is like virtual address, we will round it up to the next page, and we'll be using this variable a. So this is the virtual address, right? We'll be looking and essentially saying, okay, what is the entry in the page table? So this entry, for example, this specific entry, which corresponds to address A. So essentially we will take this virtual address A, split it into 10, 10, and 12 bits, right? So these first 10s will land us on the page table directory and choose an entry. This 10 will be used inside the page table itself, right? Page table. And this is the entry which this walk page table directory will return at this as a return value, PTE, page table entry. So if I change a pen color here, make it blue, so this PTE is exactly this blue entry, right? It's a pointer to this entry. So essentially this one is pointing right here, right? And what we're going to be doing with this page table entry is the following. We'll say, okay, look, if the entry is already present, so essentially, you know this, what the star means. It means like take the value which is pointed by the specific pointer. So it's a pointer dereference, right? And you say, does it have a PTE present flag? If it's already there, it means that something is horribly wrong. And we panic here. We say, okay, the kernel is in some completely broken state. We don't even know how we got here, but there is no even like the slightest reason to move forward. At this point, it just makes sense to just stop and don't do anything, right? However, if you say, okay, if everything is good, the page entry is not yet present, we just simply write this physical address, this physical address into the entry, right? And we're not going to write the physical address, we're going to write physical page number with some flags. Essentially, if you use an OR operator here, you say, well, this is the permission which are passed from the kernel map, right? And this is the page present flag. So it's specifically a very good thing to write into this page table entry, right? And you say, look, okay, hold on, like this is fine. So I started with the very first page and I'm going until the very last page. So it's essentially virtual address plus size -1, right? So I will end at the very last page, which is rounded down. So like I don't overflow beyond the region, right? But essentially you say like if A equals to last, we'll break. If not, we will increment the page, the virtual address and the physical address, and just go here to the next page and here to the next virtual page, right? So it's kind of a loop, which you say like, as long as I have this function which walks the page table directory, I will be just totally fine, because it will return me page table entry, this blue entry, and then I will just simply write something into this entry, like essentially virtual page number. And again, it's very similar to what you have to do in your homework. So this is how you create a page table, right? In this homework 4. So essentially you create a loop and you just map one page after another like this, right? Okay, all good. Are there any questions about it? And now the only thing which was left undiscussed is this walk page directory function, right? What should it do? And it's somewhat similar to what you were suggesting a second ago. Walk page table should return this blue entry, right? And for that, it takes a virtual address and it takes the page table. It splits the virtual address into this 10, 10, and 12 bits, and it walks the page table, similar to how the hardware would do, because it needs to return the entry, which corresponds to this virtual address, right? And for that, it will work the page table. And if this leaf of a page table is not yet allocated, if it's still null, since we're passing this flag saying, okay, please allocate the leaves, it will allocate a new leaf and will update this entry to correctly point to this leaf, right? That's intuitively, it makes a lot of sense. You say, look, I will be Like, I don't really care. Like, I just want this entry to be there and I will allocate it on the fly, right? Okay, let's take a look at this walk page table directory function, right? So it's essentially the goal is to, like, starting from this address, which is a virtual address, take these 10 bits, figure out the entry inside the page table directory, pick up the physical page number of the next entry. If this one is null, then we allocate this next level. So use kalloc, but you do this only once, right? Because first time it's null, you allocate. The next time it will be there because you're going to write it here and update the pointer correctly. Then take the next 10 bits, right? And allocate this entry in a page table, right? Okay, and then essentially you can just, this entry gets returned and you just write the physical page number and the permission bits there, right? So it seems relatively easy. Let's take a look at the code, right? Actually, those slides actually illustrate the process of mapping the page, but I already explained it to you, right? So this is the walk page table directory function. So it will do exactly this. We'll split the linear address into 10 bits, right? These 10 bits. Then it's exactly what it does here. So walk page table directory takes the page table pointer to the root of the page table, right? It takes the virtual address. This is the one we're splitting into 10 bits, 10 bits, and 12. And what we're doing here, we're using this macros, which is called PDX, or page directory index. We take the virtual address, and how do you think this macro should look inside? What does it do? Masks, right? Exactly. It will mask and shift, right? Because we just need an index. Actually, to be honest, you don't even have to mask. You just have to shift, because the right shift essentially extends everything with zeros, right? For this top 10 bits, right? Let's take a look at the implementation of this macro, right? It's defined there. So it takes the virtual address and shifts it by 22 bits, right? PDX shift is defined to be 22. That totally makes sense. They do mask the lowest bit, but that's not necessary because the rest of it is still zeros, right? For the next index, for this PTX, you will need to mask, right? Because here you will shift by 12. So it will be something like top 10 bits, all these are zeros, and bottom 10 bits, but you really need only the bottom, right? So you have to erase those ones and mask them, like essentially masking this with ones, making sure that you take only the lowest 10 bits, right? So this definition of the other macro is essentially PTX shift, which is only 12, and then we mask, right? That's correct. Okay, cool, we got it. So this is the definition of it. This macro, which essentially allows you, takes the virtual address, which is, for example, this one, takes the middle 10 bits and returns the index, right? So essentially, if those bits are like 55, it will return 55 to you, right? And then you can use it to walk the page table, right? Okay, this is what happens. So essentially, you use the page directory index. You check that in the root of the page table, this entry which got returned, so maybe that this one returned something like, this guy returned 55. This is a pointer to this entry number 55. You have to check if it's already present, right? If you're checking for whether it's null or not null, and you check like this. Present bit has to be set if it's not null, right? Okay, if it's really not null, you just simply say, look, okay, I will use the page table entry, essentially extract this physical page number from here, turn it into an address with this other macro, right? And since it's a physical address, you can't really access physical address. It has to be mapped, right? But we know that we mapped it with a 2 GB shift, so we can use another macro which converts from physical to virtual addresses. So this one actually just adds 2 GB. So if you take a physical address at 2 GB, in this specific case, just because this is how we constructed the address space, everything is mapped with a 2 GB shift, it will return you a virtual address, right? And this virtual address is a pointer to the next level of the page table, right? So this was page table directory, and this is page tab, page tab, right? Got it? And okay, that's good, right? And if it was like that, if this already existed, we don't have to allocate anything. And remember, our goal is to return an entry, right? That was blue on the previous slide. So what we do is that we say, please take the page tab, which points right here, use this macro to locate this entry and take an address of this entry and just return it, right? That's it. Because this is what exactly this function is returning, walk page table directory, right? Okay, all good, right? However, what happens if this second level was not yet allocated, right? In this case, we go to the other part of this code, right? So essentially, I discussed this macros in detail with slides, but let's just jump over. This is the explanation for virtual to physical, right? So virtual to physical is essentially, since if this one is our physical address, so we're adding 2 GB, just this is how we're mapping everything, right? So this becomes your virtual address. So virtual is equal physical plus 2 GBs, right? Just for those addresses, for the ones which are in this range, right? Which the kernel is using, right? So you can't really take a user virtual address and hope that you will use the same virtual to physical macro, because it will just again essentially subtract minus 2 GB, but really these pages will be somewhere over here. You will see how it works a little bit later. Don't get scared yet. Okay, so there is explanation for this macro, right? And as I said, if everything is there, you return it. However, if this check fails, right, then we have to essentially allocate this entry, right? To allocate it, what we do here is the following. You say whether this was set to 1, so we are actually allocating as we're going. If not, we will just return 0, right? That's okay to return 0 from this function, so nothing will get allocated. You say just no, I don't really know. The page table, the entry doesn't exist, right? But what you're doing here is that you're using your memory allocator to allocate the next level of page table. So essentially, this kalloc will allocate this. If this one was page table directory, this will be your page table. And of course, you have to update this entry within the page table directory, right? So what you're doing here is first you setting all bits of this page table to zeros, right? Sorry, to make sense, because you don't want any garbage there, right? So you have to reset it to 0. Sorry. And after that, you say, look, I will update this page table directory entry, which was right here, right? This is this page table directory entry points right here. And what you're going to write there is you say, I will take the virtual address of a page table, which points right here. I will convert it back to physical address, right? It will be physical page number, but since physical address and it's page aligned, so the bottom bits are anyway zeros, right? So you don't have to do any special conversions. You don't have to like mask them out or something like that. You know that they are zeros just because it's page aligned already. And you just set some flags here. So you set the page present flag, page writable flag, and page user accessible flag. This user accessible flag is a little bit weird because you would say, look, this is the kernel memory. So why are we even setting this page user flag? Because otherwise, like, user would go through this, like, this is page table entry user flag, and it's set here. You say user will be able to go through this entry, but that's okay because the x86 will never set a flag right here, right? So for the kernel memory, page table U will not be set in the next level. I wouldn't write it this way personally, but they did, and it's fine. So just not sure what was the real reason to do that. The real reason, maybe it was easier to debug or something like that, right? We can go through the diff, through the Git history to understand when this flag shows up, whether like it was there from the very beginning or whether they added it for whatever reason, to understand the logic behind it. So I wouldn't write it this way. And typical operating systems like Linux will never set this flag for user because they want to stop the translation as soon as possible, right? Okay, got it. But in the end, okay, this entry will be updated. So this entry will be correctly pointing to the page table directory. page table, sorry, so entry from the page table directory, this entry will be pointing from the page table. So it's totally fine. And you can actually, again, do the same logic because it's a page table. You have a pointer, everything is fine. You return the address of the entry. Let me stop here for a second. Okay, your chance to ask questions.
So we are mapping the entire, so we are allocating entire memory that we would require for the kernel.
You're saying, are we allocating the entire memory for the kernel, right?
I mean, like, so like whatever is from kern base to like kerns that
Correct.
the end of it.
Yes.
So we are mapping whatever the kernel, the fizz stop or something is there, right?
Correct. And you
Yes.
you are confused, like what's going on? Like if you're allocating all this memory for this page table, what will happen to like where we will get memory for to create processes, for example, right?
Yes.
Very good question. So what do you think? Who can tell me? If anyone has ideas. That's a great question. What do you think will happen? Let's go forward and let's find, you can scroll through those. I have like very detailed slides before I was. Okay, let me go back to show you the picture. But no idea, no one knows the answer, right? Let me just use this figure. Or this one is even better. Look, this is all physical memory on the machine. The fact that it's mapped in the address space of the kernel doesn't mean that it's used, right? What we were going to do is that right up till now, we went up to 4 megabytes and we donated those pages from the kernel end until the 4 megabytes to the physical memory allocator, right? We'll do the very same thing and donate all the other pages here to the physical memory allocator, right? And essentially this allocator will have a list here of all available free physical pages, right? And of course it will be mapped, but being mapped doesn't mean that it's being used, because the list is still like we have those pages on the list of free pages, right? Which is just great. So next time, the fact that it's mapped, it means that we can actually access this list and take an element out of the list when we allocate, or put the element back on the list when we deallocate, right? But it doesn't mean that it's used. And when we create a new process, for example, just yet another address space for the new process, we will map exactly same physical pages here as well, right? Which means that you say, look, I don't get it. Why are we doing this? Because in every process, there will be a region above this 2 gigabytes, which will represent kernel memory, and it will be identical in every process, right? This way, when you do a system call and you jump from here into the kernel, you can immediately access the same list because it will be here as well, right? It's the same mapping, right? So all the memory and all the like storage, all the bytes which back up this actual memory here will be available within every process. This is what we are doing. So we will, every time we will be creating the process, we will map, we'll invoke exactly the same function which maps those 4 regions that will create the kernel part of the address space every time. A normal kernel would do it somehow like it would share the entries in the page table. x86, again, for simplicity reasons, will just map, will invoke the same function which will allocate the leaves of the page table and a root of a page table, and will not do any sharing, right? Do you understand what I said? Or in any way, like ask another question if something is not clear yet.
So where would the user part of the memory will be used? Like how will the user part of the memory will be mapped?
Roughly speaking, when you want to get a page for the user part of the address space, you will still invoke the same kalloc, and which will return one of those pages, right? Which will be, let me change the color, which will be somewhere over here, right? Agree with this, because this is the page here, this is the page here, and you will map for the user. So this page will be actually double mapped. It will be mapped here, and it will be mapped here as well. But that's okay. There is nothing bad into double mapping the page. So this mapping will be created with PTE user flag set. So user can actually access this page and actually like execute or read or write this physical memory, right? And when the process will be destroyed, like the page table of the user will be destroyed as well. This page, however, will go back on a free list of the allocator. The kernel can still access it and can add it back on the same list, right? Because to add a page on the free list, you have to write into the page saying, okay, there is next point or which point somewhere else, right? Got it?
Yeah, got it. So
It's a little bit like you jump into a little bit. Yeah,
it will
ahead,
be
sorry.
double. Sorry, I was just saying it will be doubly mapped. That's what I got confused.
Yeah. So we will get there. So we are not yet. We haven't yet discussed how we create processes, right? But it's a good question. So I understand that it's a little bit confusing, but we are getting there, right? And I'll explain how exec works, like, or fork. I forgot what I explained. One of those two, how they work and how every page gets mapped, right? Good.
Yeah. Good.
Okay, thank you. Yeah, good question anyway. Okay, so we mapped these 4 regions, right? And I have a ton of slides, but we already discussed this in details. We kind of had the outline of everything, right? So what's the recap here? What happened? So we jumped into main. Now we created a memory allocator which can allocate pages. And we created a new page table which maps all this physical memory from 0 to fistop. We map in like as 3 different regions. One is read write, one is read only, and one is read write. And there is this strange region at the very top of the address space, the IO space, right? And this page table is actually pointed by the control register 3, right? So the kernel is now uses a complete, well-defined, well-structured 4 kilobyte pages and a page table, right? And essentially at this point, we know how to kind of create address spaces. So we're kind of ready to create processes, right? And this is actually what we're going to be doing next, but after a small intermission. So this intermission will take us through the mechanisms of interrupts, right? Because we have to understand how system calls are implemented, right? And for that, we need to understand interrupts. So let me talk just a little bit more about this main function, right? So I don't discuss every entry in the main, right? So, but roughly speaking, we discuss these 2 functions in details. Then the kernel will detect other CPUs, essentially, and you're welcome to read and understand how other CPUs, remember this one was bootstrap processor, and those were application processes. So roughly speaking, the kernel sends a special interrupt, which says, okay, start execution from a specific address, and here is the stack. And then on every, almost like on every CPU, the kernel will do a similar function, but it doesn't have to initialize like the kernel memory allocator twice because it's the same kernel memory. So they will see, I will discuss how synchronization works in the kernel. It might be a little bit confusing right now, but we'll get there, right? But roughly speaking, detect and initialize other processors. Initialize interrupt controller, we'll talk a little bit about it. Initialize segment descriptors, so essentially like construct a new GDT. Same way, we don't want to run on the entry GDT because entry like boot time GDT doesn't even have entries for user, right? It has only 2 entries and both of them are privilege level 0. So we'll have to create privilege level 3 entries. We'll discuss it a little bit more. Here's this printf, which essentially you probably see when you boot x86 if you already done it, right? So it says starting a CPU number such and such. Initialize like a little bit more of interrupts. Initialize the console so it can print on the console, right? So essentially it's a serial line and a VGA, so it's like you can see output from the kernel. UART is initialization of a keyboard. Essentially, when I type on a keyboard or it goes over the serial line, the kernel gets an input. Initialize the process table. We'll talk a little bit later about it, but essentially just initialization of saying that processes are not running yet. Initialize interrupts and trap vectors, right? So initialize buffer cache. We're going to talk about it when we reach file systems. Initialize the file table. So essentially, remember I told you that x86 doesn't really dynamically allocate process data structures and file entries, right? So this is like a table is initialized and that's it, right? Initialize disk, right? Under specific condition, it initializes a uniprocessor timer, but it's only when is SMP is off, right? But we are actually booting on a SMP machine, so the timers will be initialized as part of the interrupt controllers, right? And at this point, this is sending these interrupts to essentially wake up other processors, right? Remember, I told you that up until now we didn't have much free space. We only used the memory from end of the kernel up until 4 megabytes. So we say, look, we're gonna initialize the allocator from all the memory, which starts from 4 megabytes up to fist top. So essentially all the pages which are going up from fist top, right? Up from 4 megabytes to fist top. Now we have a ton of free pages, so we can create new processes, right? Because during this, it's actually a good question. Like I keep asking it on the exam, why can't you move this Init function up, right? It says it has a comment must come after start others, and I will ask you as well, just so you know that you understand the kernel well. So get ready to answer this question later on, but don't worry, right now it's too early. Then it creates the very first user process, right? User init, and then it jumps to MP main, which essentially will end up running a scheduler, right? And I told you that this is the stack which we created here, and on each CPU it will enter MP main here by the end of the boot sequence. And what this MP main will end up doing, it will enter an endless loop which will be looking at the process queue and picking the process which is ready to run, and will context switch to this process and will start running, right? That's essentially the entire main function, right? I understand that I only provided a high-level description, but at least you probably have a feeling that, okay, look, I didn't cheat a lot. I just said, okay, like we initialize interrupts, file system, buffer cache is a file system, right? And enter a scheduler on every CPU, which will boot in the system, right? So you kind of can trust me, okay, at this point, okay, it actually makes sense. There are no super black holes. I understand that they are gray, and I didn't explain them in videos, but you can at least believe me that it's believable that it will run like this, right? Okay, let me stop here again for questions. Anything to clarify?
So this like every processor will have its own set of registers, and all the control registers are also different for every processor.
No, control rate. No, like when we're going to be doing context switch, since we have to switch from a page table of one process to a page table of another, we will reload the control register 3, for example, right? We'll take a look at the context switch. And of course, you will save and restore all the general registers. And I don't think we were going to be reloading the global descriptor table yet, but we will be patching one entry. So essentially one entry of the, it's called task TSS, task stack. I forgot what TSS stands for, but we will need to update this pointer, because the pointer will contain it will contain a pointer to the kernel stack of the process, right? So every time we're going to be switching between them, we'll be changing this pointer.
Okay. So the MP init will be initializing what will be doing it? What will it be initializing in the other
Let's take a look
process?
if I have a couple of slides.
Okay, fine.
So this one is specifically about seg init. Let's go like through a couple of those functions. I didn't plan, but if you want to know this detail. So this initializes a segment descriptor table, right? So The CPU ID function returns a ID of a current CPU. On a CPU 0, it will return 0. On 1, it will return 1. On 2, it will return 2, right? And so x86 has an array of CPUs, right? And essentially each CPU will have some private state, right? And there are different ways to structure this code, and it used to be different in x86 as well, but this is how it is structured right now. So it's essentially an array, and then if you want a data structure from a specific CPU or a per CPU data structure, you just take a CPU ID and essentially land on the entry in this array, right? Okay, sure. So we got the CPU. Each CPU has a global descriptor table, right? It will contain just a couple of entries, right? We don't need a lot, right? We need an entry for kernel code, entry for kernel data, entry for user code, and entry for user data. And the difference between them is these kernel entries are mapped with privilege level 0, and user entries are mapped with privilege level 3, right? Or DPL, descriptor privilege level user, right? And of course, the code is executable, data is writable. Code is read-only, data is writable, right? So, and then you say, look, please load this GDT on this CPU into the hardware register, right? Which keeps a base of the global descriptor table. So this is how this works, right? And as I was saying, right, so this is the CPU data structure itself. It has a pointer to the scheduler context. We'll discuss about it. We'll have a pointer for the task state, right? Again, we'll come back to it, right? And the currently running process, for example, is there, but this GDT is essentially an array of n segments, right? So not many, so like maybe like 4 or 5, right? We discussed 4, but I bet that there will be at least 5 because we need TSS as well, I'm pretty sure, right? And we talked about the segment descriptors before. Remember when we were booting, so essentially we were using this assembly macro, but now we're using a similar macro. And the reason is to use the macro is that just because this, you know, the limit is, the base itself is split, right? So base bits from 0 to 15 live here, from 16 to 23 live here, and from 24 to 31 live here, which is a little awkward, right? And like doing it in human, like manipulating those bits by hand would be awkward, right? It's very easy to make a mistake. So it's convenient to have a macro which like load, like initialize this entry with correct values. Similar for the segment, for example. So some part of the segment limit, similar for the limit lives here, and upper bits of a limit live here, right? So that's why limit is convenient, right? And this is how you define this in C. So essentially you use this, C allows you to use bit field. So essentially you say like, this field is actually 16 bits, this field is 8 bits, this field is 4 bits, right? And this is the layout, and the compiler will preserve this layout in memory. So this is the beauty of C. Other languages have similar capabilities, right? Sometimes you have to add like a specific flag, some kind of like a pragma here to say something that, okay, it's a C layout and stuff like that, right? And okay, so I actually didn't have a slide on initializing of MP entry. I thought I did. So what MP Init will do is MP Init will detect the presence of other CPUs in the system, right? And you can go and read through this code, and maybe the book covers part of it. And I can essentially, I can prepare tiny, like a couple of slides on the topic, just to make sure that we go through it if you care about it that much. But literally this function is here, and what it will be doing, it will essentially will be communicating with local advanced programmable interrupt controller, right? And we'll be reading various values from it. So to make sure that you will figure out that the CPUs are present and are ready to run, essentially, right? So for example, default value, SMP is off, right? So if you didn't find anything like that, if you say, look, from observing, looking at this table, I see that there are no other CPUs, we'll boot on a single processable, single CPU machine, actually. It will not boot, it will say panic, didn't find a suitable machine, right? right? So I didn't explain much about it, but it's kind of like a dark magic, and you have to like read through the manual to understand what's going on here. I didn't want to spend a lot of time on this, but you're welcome to like go for it and ask more questions, and I can provide some reading material for that. Is it something what you cared about? So, or shall I stay more on this subject or move forward?
I think reading material should be fine. We can go through.
Yeah, okay, good. But it's relatively easy, and I will probably talk about how this interrupt is sent and how the CPU is woken up and how we start running on other CPUs when we get to scheduling, right? But right now, just trust me on this, and let's like move forward. And our next subject today is actually interrupts. So we are ready to essentially switch to the next lecture, which is right here. And essentially the idea is to discuss how interrupts are delivered and how interrupts are used for implementing system calls, right? Okay, sure. So as I was saying, we're still running inside main when we initialize interrupts. If I ask you a question, why do we need interrupts? Who can tell me? What are the ideas?
We need to change the hardware ring level.
Hardware privilege level to securely enter from user to kernel, and essentially to implement the mechanism of sys calls, right? System calls, right? That's one use. What other? What else we can do with interrupts?
And some IO device for to implement, like, so whenever to send
Correct.
data,
So
or
for example, a network packet arrives on the wire. The logic of the device, which runs a tiny operating system on its own, but it's typically called firmware, but okay, it can be x86 actually, why not, right? So it uses a DMA mechanism to place, DMA means direct memory access. It looks very fancy, but it just simply copy in memory without touching the CPU. So essentially, if this is your physical memory, this packet which arrived, like this is the packet, it arrived, it got copied over here, right? And typically you operate in batches of multiple packets. So maybe like, you know, a couple of those packets arrived on as sitting in memory. But at some point you say, look, it's time to let the operating system know that new data is available, new packets are available. So this device raises an interrupt, and the execution of the CPU switches from whatever it was running right now to executing an interrupt handler. And this interrupt handler might very well just like copy those or like process those packets, like turning them into like essentially messages or entries in the socket buffers to make sure that if it's a networking, then, you know, the application which was waiting for this data can actually start accessing, right? So it might copy it into user memory to make sure that it's available to user, right? So this is how it works. So like an alternative idea is, imagine it's not really like a complicated network interface, but something like simple as a timer. And you say, look, periodically, we want to receive an interrupt from a timer. Why is that? Because maybe user runs an infinite loop and it will never enter the kernel again. Maybe it's a bug, maybe it's a feature, maybe it just, you know, like, maybe it just computes some very long, you know, sequences or whatever, like of pi, right? And to make sure that the CPU is shared in a fair manner between multiple processes, periodically the kernel will receive a timer interrupt. An interrupt is similar to the interrupt from this network interface. You switch to an interrupt handler will switch to an X process, and we will take a look at how it works, right? But this is more or less the 2 or 3 main reasons. So you do syscalls, you really receive asynchronous notifications from IO devices, and you receive interrupts from timer, which is kind of like a IO device, but it's a little special. That's why it makes sense to talk a little bit, to talk about it separately, right? Okay, sure. So as I was, I actually missed one important reason as well. So I say 2 main reasons. The reason which I missed is something like a page fault, some catastrophic event in the environment, right? So essentially, either you're dividing by 0, maybe it's an overflow, maybe you're trying to access a page which is not mapped. At this point, you know, the operating system has to know what's like maybe you have to fix the page table. Maybe you just swap this page out and you will swap it back in, but it's called the synchronous interrupt. So essentially something bad happened and OS needs to fix it, right? Asynchronous interrupts, I just discussed it. It's like network packet arrived or a timer interrupt. And then a third special case, which we discussed, is a system call. So essentially you also use a synchronous interrupt. So you can essentially invoke an instruction saying, please use interrupt number, what is this, x80, right? And that will take you through the interrupt descriptor table to the handler for the int 80, right? And this allows you to transition securely from the user level to kernel level. Okay, let me take a look at how it works. So how do we handle an interrupt? I'm coming back to this wonderful figure, which I was using in the beginning of this class, and you probably would like, you already forgot about it. It looks a little goofy, but nevertheless, normally CPU executes instructions one by one, right? So we generate the instruction pointer, we read the instruction, so essentially fetch it from memory, whatever the bytes are here sitting, right? They got fetched to the CPU, right? It's done like in a speculative manner. There are like instruction fetch queues, which try to predict branches and fetch as many instructions in advance as possible. So you don't have to wait here like 200 cycles, which are required to access memory, right? So everything is like kind of cached in L1, L2, and L3 caches already, right? The next thing, we decode the instruction, right? Essentially understanding whether it's a move, addition, a jump, or something like that, right? We do a register read. It's a little bit low level for this class, but essentially it's like a separate phase of the execution of a pipeline. And then we execute this instruction. Maybe we did the addition, right? And at this point, so maybe it was a move instruction which touches the memory and the page is not mapped because this PTE present bit is not set, right? It's 0 and it generates a page fault, right? Or maybe it's a division by 0, right? And you have to stop it because you don't really know what to do at this point. And normally you would commit this instruction, right? But in our case, if it's an exception handler, you don't go to the next instruction, but you start with this. You say, I will write some fault data to the exception registers, right? What does it mean? Okay, let's skip for a sec. I will locate the current exception handler. So essentially, operating system will maintain a special table in memory. So it will be somewhere here in memory, right? Somewhere in memory. It's called interrupt descriptor table, right? So, and depending on which interrupt, so maybe it interrupt 0, interrupt number 25, it will choose an entry in this table, right? And an entry in this table will be configured by the operating system, and it will be the instruction pointer of the first instruction of the interrupt handler, right? And security reasons, maybe user reloaded the stack pointer to point, like, for example, to address 0 or to some unmapped page, right? Or maybe point to the data structures within the kernel, right? So if you switch to privilege level 0, you will be accidentally able to override those data structures in the kernel with whatever the hardware will save on that stack, or maybe your interrupt handler will save on that stack, right? So it's not safe to continue on the same stack, right? And that's why the hardware will choose a new stack, which operating system configures beforehand to make sure that we're not going to use this untrusted user stack because we can't trust the value of this pointer, of the stack pointer, but instead we'll be using a register, right? And why do we need this stack? Remember, we skipped this first step. So right now, our instruction pointer is pointing to the interrupt handler. But obviously, at some point, we want to return back from this interrupt, right? So we need the instruction pointer of the user, this one. Let me change the color of this. Let me make it blue, for example. This user instruction pointer, right? Hardware itself will save it on this new stack. So this user instruction pointer will be here. But remember, we temporarily saved it inside internal CPU registers. Why? Because this stack which we're using here was not yet located. So that's why a couple of things first get saved in the registers on the CPU. Those registers are not visible to us operating system developers. It's just handled internally by hardware. But then there is like several of them show up here. Those are the registers which are changed immediately during this interrupt transition, and they have to be preserved. And I explained what these 5 registers are, so you will understand what these are, right? Okay, so but we are now ready to push this instruction pointer on a stack. Let me erase everything from this slide, right? So we pushed stack pointer, instruction pointer, and a couple of other registers here. So essentially at this point, you update the instruction pointer to point here and stack pointer to point here, right? Okay, so that's a high level idea for the transition. Let me stop here again for questions. You got the point that nothing magical, like CPU doesn't change. It will continue the same fetch, decode, register, read, and execute loop, right? It will just start executing. It used to execute somewhere, okay, instruction pointer somewhere over here, right? And during the interrupt, the hardware just saved this old instruction pointer, which was pointing here, saved the old stack pointer, right? And started executing instructions from here, but it's the very same loop, right? So there is no specific pipeline inside the CPU which executes this interrupt handlers. It's all the same. Just we'll change the privilege level, save something on the stack, switch to a new stack, stuff like that, right? But okay, let's take a look at details. How does it really work inside the operating system kernel? I wanted to also make sure that handling interrupts and exceptions, and what's the difference? So exceptions are typically called synchronous interrupts. So like division by 0, what does it mean synchronous? You execute an instruction, like something move, and it tries to access an unmapped page of memory. You have to trigger exception just because you don't know what to do, right? It's invalid state. You have to stop here. And interrupts are typically asynchronous notifications from devices, like from network cards, timer, stuff like that. But both of them are handled through an identical transition, which I just like described to you, right? And at the high level, it's like stop execution of the current program, start execution of the handler with all of the saving and restoring of stuff which are in between, right? What's also important is, like I said, that interrupts are identified by a number. So for example, interrupt number 14 is a page fault. Those interrupts are reserved by Intel, right? So you can't really change them. So interrupt 14 will always be page fault, and you can't really like assign an asynchronous interrupt from the device to that range, right? That doesn't work this way. So 3 is a debug interrupts, essentially. This is you can say, I will write a specific XCC instruction inside my binary, and next time the program reaches this instruction, it triggers a debug interrupt, right? So essentially, this is how GDB installs a breakpoint. There are multiple ways to install a breakpoint, but there are hardware breakpoints and there are software breakpoints. So this is a software breakpoint, but they are faster, right? Because you can only have like 4 hardware breakpoints, and you can insert unlimited number of these XCC instructions in your code. And then what happens is that whatever was their original instruction is single step, is put back by the GDB, and GDB just single steps. And there is a specific hardware mode saying execute one instruction and get another debugged exception, right? So a single step. So that's why you can single step programs essentially, right? Okay. When you execute an interrupt, there might be 2 cases. One requires no change of privilege level. So for example, the CPU is already running inside the kernel code, right? You already did a syscall and you're running inside privilege level 0, right? And then interrupt comes, and depending on how interrupt descriptor table is configured, you say, look, I stay within privilege level 0, right? And at this point, there is no change of privilege level. Alternatively, however, interrupt does change privilege level. So for example, you're running inside user code, right? Privilege level 3. And then the interrupt transition might take you from privilege level 3 to, for example, privilege level 0, right? Because the kernel has to take over maybe context switch from one process to another if it's a timer interrupt, or maybe update a mapping in a page table reacting to the missing page, right? Okay, let's first consider the first case. It's a little bit simpler. right? It's a case where interrupt path does not change, does not require privilege level change, right? So we're already running in a kernel, right? Then actually I told you that we need to switch the stack, but in this case, we don't really need to change the stack because we're already in the kernel. We trust the kernel will not abuse the stack, will not do anything to the ESP pointer, right? So what happens is that the interrupt vector itself, right? So for example, a timing interrupt is a vector 32, right? So, or there's this terminology for IRQs, which start like if interrupt vectors go from 0, right? So the first 32 are reserved by Intel for something like page faults, division by zeros, right? So this is 31. So, and the next 32 are typically assigned to IO devices, and they also kind of like assigned according to a specific standard, right? So in this IRQ0, which is vector 32, so this is IRQ0, the next will be IRQ1, IRQ2, right? This one, this IRQ0 is an interrupt, is a timer interrupt, right? That's again the convention, right? And so what happens is that you receive this interrupt number 32, right? So you go into the interrupt descriptor table. Here you will have a pointer to the handler, right? So operating system will initialize this table. We'll take a look at how it's done. And you start executing within this kernel, within this handler, right? What needs to happen is that you have to configure the interrupt descriptor table, right? And it's kept by the hardware in a specific register, which is called interrupt descriptor table register, right? It contains the base of the interrupt descriptor table and contains its size, the limit, right? So, and essentially you do the checks, making sure that, okay, you note like the interrupt is actually has an entry in the interrupt descriptor table, right? And it contains, each entry in this table contains a specific interrupt descriptor. What is it called? It's called a gate, right? And like, just don't get confused that this interrupt descriptor table register, it's part of the CPU, and the table, interrupt descriptor table, is just an array in memory, which is just pointed by the CPU register, very similar to how global descriptor table was pointed by this GDTR register, global descriptor table register, right? Each descriptor, this interrupt gate within the table, as I was saying, roughly speaking, it contains the following entries. So it will contain 32 bits of the handler pointer, right? It will contain some additional fields, like it might select, and we will take a look at this when we'll start talking about interrupt handling when the privilege change is required, right? And other flags we also describe. So like right now, just think of it that you got the point that it has a pointer to the interrupt handler, right? So essentially a table itself has a bunch of entries. Each entry is a pointer to the interrupt handler, right? So far, so good. So any questions about it? Good or too confused? But nothing really super hard happened so far, right? So just the transition, right? As I said, we're going to walk through those fields gradually, right? And interrupt handlers are just the same plain old C code. You need a little bit of assembly just to make sure that you save all the registers, because remember, I said that the hardware itself will only save the stack pointer and the instruction pointer. If you care about restoring other general registers like EAX, EBX, ECX, and so on, you have to save them in the assembly part of the interrupt handler, right? And we'll take a look at how it works, right? Just don't worry, but just have a general idea about it, right? So it's first a little bit of a tiny assembly prologue, and then like normal C code, right? So, and it lives within the kernel data section. Again, nothing super special here. This is the entry, handler address, and this is the beginning of the handler, right? For example, a timer. Okay, so let's just get a little bit specific about what happens on the CPU when you process an interrupt which doesn't require a change of a privilege level. So I talked about it, but it was a little bit informal, right? So now more formal. So what the hardware will do, it will push the following three things on the stack, right? It will not only push the instruction pointer, but in a code stack, right? Code segment, sorry, because maybe even without changing the privilege level, maybe you're changing the code segment. Never happens in practice today. Today, the code segment will always stay the same, so don't worry about it, but the hardware still pushes it, right? And the e-flags are saved because the transition through, like when the interrupt is triggered, you have a freedom of choice and you can say whether the next interrupt will be disabled at this point or not, right? And the way you disable interrupts on Intel is that you set a specific flag within the e-flags register, right? That's why you have to save the old value, because the old value, you don't really know whether this bit was set or not, right? So if you say this bit will set and I will disable interrupts, and on the exit from interrupts, you better restore the register to this state it was. That's why e-flags is also saved on a stack, right? Okay, some interrupts push an error code, not all of them, on a stack as well. So it might be yet another entry. So we have three which are always pushed, and this error code is sometimes pushed and sometimes it's not pushed. And after that, okay, we load the segment selector. Remember, I told you that the entry in the interrupt descriptor table will have this code segment selector, right? So for the new code segment, so maybe interrupt jumps between the code segments. Again, it never just jumps in practice today, it's just the same, but it will jump when we will be switching from privilege levels, right? From 3 to 0, for example, because it will be a new code segment, right? So it will have a privilege level 0 instead of 3, right? And if the call is through an interrupt gate, we clear the interrupt flag in the e-flag register, right? So essentially clearing this bit which I was talking about, disabling subsequent interrupts, right? And then we begin execution of a handler, right? Okay, let me stop here again for just one last minute because it's we're almost at the end of our class, but let me stop for questions here. Okay, good. Okay, so we'll come back to it, but this is how the stack looks like, right? If ESP was here right before we started executing the interrupt handler, we definitely push this three, the hardware pushed the three things on the stack: e-flags, code segment, EAP, and for some interrupt, it's possibly push the error code, right? But after that, you execute essentially the handler and start running here within the kernel, right? Maybe you already were running inside the kernel, but maybe you were running somewhere over here. So that's your old EAP, right? Okay, so far so good. The question is, how do you return from an interrupt? Use this IRET instructions. Essentially, IRET like saves this, take this saved values from the stack, so code segment, instruction pointer, e-flags register, right? And restores them again. If the privilege level change is not required, those are not saved, right? So you don't really have to like do anything, but those ones are restored and you continue executing from the point at which you were interrupted, right? Is it clear? So it's essentially, if you're running the user program, or that would require a privilege change. But if you were running inside the kernel, an interrupt came, you executed the handler at the end invoked IRET, and you returned to exactly the place at which you were executing before the interrupt, right? Okay, so that kind of makes sense. And I will stop here and we will start next time from discussing what kind of processing is required in case the privilege of interrupt processing is required in case the privilege level change is needed, right? Okay, so let me stop here. Again, if there are any last minute questions, I'll take them now. If not, I'll see you on Wednesday. We're good. Then thank you, everyone. See you Wednesday.